where this comes from is just the idea that if I were to it's what allows me to do inference in any way that I possibly might want to. So I'm assuming here that there might not be a population, there might not actually be a population that I can talk about, as there being kind of some endpoint. So I might want to do inference about any kind of finite sample bigger than what I've observed, something like that. And in that case, if this condition is met, then the way that I would do inference is just I would estimate the model, or I would do an estimate based on the data that I've observed, which is by picking an optimal candidate distribution from the models for data of size m. And to do inference, I would take the subset of all models that I've specified for size n, and I would just pick the set of such models that would correspond to the inferred optimum p hat under this sampling scheme. So this is a set of distributions in general. It would be a singleton only if the model was identifiable. Yeah?
So your definition looks kind of like no matter how you project, you get sort of the thing that you want after the projection, right? Mm-hmm. So in that sense, it seems kind of reminiscent of, the Kolmogorov requirements for consistency.
So it's related to that, except it's a little weaker than that, actually, because all this is saying is that the sets are equal. So Kolmogorov's condition says that if I have a distribution, that it projects to a specific distribution, and those distributions are equal. So this is saying that as a set of distributions, it projects to this set of distributions, but it need not. But the way in which I get there need not necessarily be. So there will be a consistency condition in that there will be distributions in one that correspond to distributions in the other through this sigma. But you don't actually have to specify that outright. Okay. In other words, and also in Kolmogorov's setting, that's why. So in Kolmogorov's case, these are really all. This is kind of all that was needed. These projection maps, because that's. But this is so that as I was talking earlier, as I had a conversation earlier, which is that this is taken as the default kind of sampling in theory. In theory, and it's in Kolmogorov in probability theory, this isn't to be thought of as sampling. This is just these are the projections that generate the cylinder sets that generate the sigma field, right? But then when we bring this into statistics, we try to interpret this as a sampling mechanism. But that's not it's not really how things. It's not really reminiscent of a sampling mechanism that's actually used. So what I'm trying to do here is to loosen or to generalize that idea, and it's very much related. It's very much motivated by this idea of consistency. Yeah. But it allows for different. It allows me to put something random in for this sampling. Is that Sherry? Okay. If there's still questions, of course, let me know. Okay, now I don't know to the extent to which this. So under this condition, for one, under this condition, I know that this set will be non-empty. So I know that I will actually be able to do inference out of the sample because I know that there will be something in here that corresponds to whatever I've estimated. If I wanted to do inference, for some reason, into my sample, I could also do that. I can't think of a situation offhand that I would want that this would necessarily come up, but there might be cases. But if this condition is satisfied, then I know that what I would end up with would also fall in my specified model. Okay, so the idea behind coherence is just that the idea behind coherence is that it would allow me to do inference in a systematic way. It doesn't necessarily say that the inferences are good, okay, but at a minimum, it at least says that I can do it. Okay, and that's the first step, I would argue, to being useful. Okay, so any questions? Yeah.
So even if you did not have coherence as you define it, as long as you know the sigma operator, what it is doing, you could always have this way of computing the distribution given the distribution on M. knowing what sigma is, you could compute what the distribution is on n. May not be the same as, but that's good enough, isn't it?
Well, so you would have, the question is, how did you get your estimate? So what in the case that I'm talking about, I have this set of candidate distributions, and there's only one set because no matter how I thought about getting my data, this is the only set of candidates. But you could potentially have sets that aren't that disagree with one another. But I mean, if that wasn't an issue, then yeah, what you're saying is fine. Yeah. Okay. Okay. So I have the. I want to go over time. Okay. So now, to try to convince you that this is something that's actually maybe practically relevant. This is something that is virtually seems to be virtually unknown, and in some cases seems to be ignored in the modern literature on network analysis. Of course, the effects of sampling in network analysis are well known going back to the 70s in the social networks, social science literature by Frank and co-authors. But it hasn't been until recently that the issues having to do with sampling have been kind of brought into the more modern literature on networks. And I think that a lot of this also has to do with some misunderstanding as to the implications of exchangeability in this setting. So the assumed setting that I'm talking about here is I'm assuming, as I have been the whole time, that I have a population structure, a population network, and what I observe is a sample from that network and a typical statistical situation, which is that I want to use that sample to say something about the population. Okay. And the first example that I want to give is a scenario where I'm using the exponential random graph model to do this inference. Okay, so the exponential random graph model goes back a long way. It was one of the earliest models for networks from the 80s. It's an exponential family distribution. We specify some sufficient statistics, and then we just do this exponential weighting to define the distribution. And so it was at first appeared to be a very flexible model because it seems seems like you can account for a lot of different structure that you might be interested in through these sufficient statistics. And so what might be a typical approach is that let's suppose I'm interested in doing that I'm going to specify my population model from the exponential random graph model with some parameter theta, but I only observe a sample. So a typical approach would be to estimate theta from the sample. So I fit the same exponential random graph model to the sample, and then whatever estimate I ended up with, I would use that as my estimate for the population parameter. But this is at this point known to not be. This is known to not be a. This is known to not necessarily make sense in all cases because of the theorem from 3-4 years ago from Schalese and Rinaldo, who were studying this idea of consistency under subsampling in the exponential random graph model, and they showed that in my language, that a model which takes the exponential random graph models as its candidate distributions and assumes this selection sampling, these projections as the sampling scheme, would be coherent only if the sufficient statistics have a property called separable increments, and that's a very strong condition on the sufficient statistics, which more or less restricts the model to only accounting for very localized structure in the graph, in the network. And that's generally not what these models were originally seen to be most useful for, because it really limits the scope of what these sufficient statistics can measure. And so the consequence of that is that if we're assuming this model, then the exponential random graph model for the population is parameterized by theta. So that means that in principle the sample network is also parameterized by theta, but it's just not clear how that parameter for the sample is related to the population. And so it wouldn't be clear if I were to do inference or estimate this parameter for the sample, how I would get back to inferring the population parameter.
But are you asking for an exact correspondence, or would you be happy if what you infer for M tells you something accurate to what happens with N when both M and N goes to infinity? Sorry for interrupting.
Well, I guess that gets to the question of asymptotics that I would have to, so generally I don't understand, I guess I don't know what that means, right? Because if as n goes to infinity, what is this, I guess that's kind of the whole.
If you have a graph model for any n, you get that n.
Oh, right, so I think that, okay, so I think that my answer, just to be quick, I think my answer to your question would be that I would not be happy with that, but there's definitely a lot of people who would be. But that's kind of the whole point of what I'm trying to say, which is that if I'm doing inference from, so I'm not against that asymptotic approximation, but I'm trying to understand, and that's part of why what I'm trying to get at, and I don't know the answer to it, is in what sense would such an asymptotic statements for such models allow us to do these approximations?
Well, it's when the error that you make because you switch from a reduced model from big model to a reduced model is when this error is smaller than the one you're making anyway by estimating a parameter.
Yeah, so I don't think I don't think that error is. So I don't think that such errors have been actually worked out for these purposes. At least none that I know of. But if there are, then I won't hear. Okay, so in that case, it wasn't clear what to do because well, one thing, this coherence wasn't satisfied. So without that, it becomes hard to actually proceed any further. Something that I'll go quickly through because I want to get to the third setting, which is another class of models that has become popular over the past several years are these graphon models, or vertex, or models that are exchangeable with respect to relabeling of the vertices. So effectively, these are glorified Erdos-Renyi models. So an Erdos-Renyi random graph is one that we just flip a coin IID at each pair of vertices, and we put an edge if it's heads, no edge if it's tails. In the graphon model, we associate a random probability to each edge. We do that by assigning a random effect to each of the vertices. And we make the random probability by evaluating some function phi, which is called the graphon. We evaluated at these random arguments. And so the model has nice theoretical properties. We can write down its distribution in very enclosed form. And it implies this property of exchangeability in the sense that the distribution assigns equal probability to two graphs that are isomorphic with respect to relabeling of the vertices. Okay. And so one of the main consequences of this assumption or this property of exchangeability, and this is called the Aldous-Hoover theorem, which says that every vertex exchangeable model on one that is assumed to have a countable population of vertices is a mixture, can be expressed as a mixture of graphon processes. So we assume that we first chose this phi randomly, and then given that we generated according to the same scheme as on the previous. Okay.
What is a random? I mean, what is the distribution of random functions?
What is the distribution? So
yeah, what is the probability theory about the probability distribution about random?
Well, this is just an existence statement. So what this just says
there exists a probability distribution
on the space of functions, such that I can choose a function phi from that distribution. Then, given phi, I can generate a random graph according to this procedure. So this is just a two-dimensional version of Di-Finetti's theorem. Di-Finetti's theorem for IID sequences says that there's a random measure on, so if we're doing 0-1 value sequence, it says there's a random measure on the unit interval such that I generate a random number in the unit interval p, and then conditional on p, I have an IID Bernoulli sequence with success probability p. This is this instead of p, what we have here is actually this random function. Okay, and so one nice thing about this consequence is that if we were to assume this property of exchangeability, and that means we're in this setting of graphons, if we were to think about sampling so doing projection from a large graphon process to a smaller one, what we end up with is a graphon. And so these models are actually coherent, and we can in principle do estimation from these class of models. But the issue that comes up as a practical matter, so this would satisfy my property of coherence, but it wouldn't. It's not completely satisfying because there are practical issues that make these models these models don't really fit the data very well. And the reason why they don't fit the data, one reason why they don't fit the data very well is that this assumption of exchangeability is not, so exchangeability induces some assumption about how the data is being sampled, in the sense that it's more than just an invariance under arbitrary relabeling of the vertices that we observe. It's actually a statement about the relationship between observed vertices and unobserved vertices, in the sense that exchangeability means that the vertices that have been observed are exchangeable with all vertices in the population. So in other words, what we're actually looking at is a representative sample from the population. And in most of the networks applications that people are interested in these days, that's just not the case. Most of the time, what we see somehow depends on the sample that we see actually depends on the network in some way. It's not just a simple random sample of vertices. Okay, so I'm actually I'm already out of time, but I will go quick. There's been a lot of questions, if I could take a few minutes. So a third situation, so I just want to highlight this, which is that, so my argument would be, so my thinking is that one of the main obstacles to analyzing, or to analyzing new data sets, is that what we want to do is we want to find a way to use old tools to apply to new problems. But I think that in some cases there's an obvious limitation to that. But I think that in some cases it's just not. The issue that comes up is that by using the old perspective or using existing approaches, that kind of forces us to look at the data in a certain way, and that perspective, that kind of imposed perspective, is it limits what we're actually able to see in the data. Okay? And so an example of this is in generally a lot of network data sets are formed by observing interactions in some population. So a simple example of this would be if we were to be observing, if we were to have a database, say a database of phone calls. Each entry of the database records a lot of information about each call, including the caller and the receiver, time at which the call was made, and so on. But I'm only interested in, let's say, the structure of how people interact in this database through phone calls. So I sample from the database. I observe a sequence of edges. These are just caller-receiver pairs. And I can actually represent the structure among these caller-receiver pairs. There's a one-to-one correspondence between this structure and the sequence by labeling the vertices, having a directed edge from caller to receiver, and labeling the edge according to at what point in the sequence it was observed. Okay, and so there are many data sets, network data sets these days, that might be put in this frame, in this setting, which is that these are effectively interaction networks, which are obtained by sampling interactions in the population. And so the key point here is that the focal point, or the way that these data sets are actually obtained, is by sampling of the edges of the graph. And so that somehow that context, so that actually dictates the context that, and that should be, that should somehow affect how we model the data. Okay. So one assumption that I might make, and it might be justified and it might not, but if I were to be sampling from the database uniformly, sampling entries in the database uniformly, then what I obtain is a representative sample, but a representative sample of edges. Okay, and so the sequence of edge pairs would be exchangeable, which would make these structures exchangeable, but with respect to relabeling of the edges of the graph. And another observation is that since I'm only interested in the structure of these phone calls, is that once I actually represent the structure in this way, the labels that I put on the vertices actually convey no information. So if I were to just say to you a phone number, 555-1234, it doesn't actually say anything to you about anything, right? What you care about is how that vertex is interacting with the other vertices, and that's already encoded through the edge structure. And so the sufficient information really is conveyed just by this equivalence class of graphs with the vertex labels removed, so these edge labeled graphs. Okay, so that's what would give, in this case, a different picture of how to represent these data sets as edge labeled graphs, and that gives a new or a different invariance principle of exchangeability with respect to relabeling of the edges. And so we still have some exchangeability, but it's with respect to labeling of the edges, and so that actually gets out of this limitation of the vertex exchangeability, which assumed I had a representative sample of the vertices. Under this condition of edge exchangeability, the vertices are the vertex that appear in the vertices that appear in the sample are actually a size biased sample according to the degree distribution. Okay, so there's various practical benefits as well that I won't talk about. But yeah, one question.
So I'm sorry. I don't understand why you change the order, because if you subsample, so if you have a subnetwork with some number for the edges, if you subsample, you would reorder the edges 1 to m according increasingly, but according to the order of the previous calls, if you want to keep the same call order. Because your order on the edges was the same, so
I'm assuming, so for the purposes of this, I'm assuming that I'm not taking that into account. Yeah, of course, if that was relevant information, I would be able to. Okay, let me wrap up here, which is just to say there are other contexts in which I think it would be useful to. I guess the point I would make to anyone who's working in networks, and those of you who are engaged in networks, is that it would be interesting to see how some of the theory for networks would play out if we were to get to expand beyond the current picture of thinking about networks specifically as just graphs with labeled vertices, and thinking of them as growing one vertex at a time if we were thinking about asymptotics. And there are several new proposals for that, for how we might think of networks from a different perspective, and perhaps they would give insights that we currently don't have. And so I could, so this was just a summary of the conclusions, which I will skip unless there are questions. Some more of this, so more information can be found in some of these papers that this has been part of a collaboration with Walter Dempsey, who's over the past several years, and I'm also, some of these topics are also part of the book that I plan to finish, that I will be finishing in the next month or so, should be out in the summer on network modeling. Okay, so thanks a lot.
Any questions?
I think one of the issues with this, defining a population basically when you're talking about networks is somehow the distributions of infinite graphs. So it doesn't seem easy. I mean, I don't know much about this stuff, but it doesn't seem very easy actually to put down a distribution for a graph and an infinite number of nodes that somehow satisfies sensible properties. And for example, the exchangeability version, right, where you basically want a probability measure on infinite graphs such all of the vertices are exchangeable. that seems to lead to nonsense basically. Or if you subsample any of those, if you subsample this infinite graph, you end up with an empty graph. I don't know if you have any thoughts on that.
Well, with respect to specifying a model on an infinite space, a graph of infinite size, usually the way it would be done in practice would be through appealing. Usually it's done in practice by appealing to this idea, this Kolmogorov idea, which is that you would specify each of the finite sample models, and that in principle, since they fit together in a consistent way, that does induce or uniquely identify a distribution on infinite graphs.
So I thought there were convergence issues with that. So you can easily define a sequence of probability models on graphs, but is it always the case that that sequence converges?
And it has to be tight. There's an additional constraint for that.
Right.
But I think there are models.
So specify. So I think that we're talking about two different things, because in specifying a model, asymptotics doesn't come into. It doesn't. It's not asymptotics in the sense of taking limits, in the sense of convergence.
When you talk about a population, you mean an infinite population, right?
Well, so that's why I was hesitant to kind of. That's why I wrote it this. That's one of the reasons I wrote it this way. Although this is a bit in the weeds, but to the question that was asked is that.
It was only me who said infinite. Nobody else.
I don't want to. I don't actually want to impose that the population is infinite, because that's kind of a meaningless concept. But in general, I don't know what the population size is, so I would specify models for every hypothetical finite sample size. But in any case, it's really not. But the point is that I think that maybe we should talk more about this afterwards. Whether or not this can be done, or whether or not this makes sense, I think does tie into whether it's the consistency issue or this issue of coherence. There's one in the back. Yeah.
Can you get a lot of the results you want if you just have containment of your sigma to mm? Do you actually need equality?
So I think that, so I've thought about that, and I'm going back and forth as to whether or not which you would choose. I think that you could play around with containment. I think that I think that you would want this condition to certainly hold, so you would have.
Right, but the top condition, can't you just get containment in this direction, that when you project it's a subset of m sub little m, and that's enough?
I think that's not enough. I think that would lead you to a problem, because this set could then be empty. I think you want containment probably in the other direction.
But then that would lead you to a problem, right? Because then it suggests that m sub m, when you project, you get things that are potentially not even in m sub m, right? And that's bad. Because
yes,
then you
okay,
get
so now you've answered my question. This is why I put equal.
Okay.
Yeah, I've gone through this, yes. But it would be nice if you could do something like what you're saying, because this would weaken the condition, which is already a very strong condition. But I'm open to suggestions there. This is kind of what I'm at. This is where I stand today. Okay, sure.
There's refreshments where you can catch hold of Harry. All right.
Okay.
Let's thank him.